So we'll try and live up to being fantastic speakers, so I might as well kick it off here. So one of the more infamous PhD students back when I was in Australia doing my PhD underneath Richard stated in his PhD that in the field of hypersonics, all the low-hanging fruit had been picked, and that his work was really, a difficult problem because the previous generations had picked all this easy low-hanging fruit, and only the difficult problems were left to be solved. I'm hoping after this talk we can convince you that it's only that we can pick any fruit at all these days is because we're standing on the shoulders of giants. So just to give you some of the context and some of the background, I'm going to let my mentor in hypersonics, really, Richard Morgan, speak about some of the background for why we need to build high-speed wind tunnels, and give you some of the history behind the collaborative nature between our lab down at Osney Industrial Estate and with the groups in Australia. And I'll come back on at the end to speak about our newest high-speed wind tunnel, the T6 Stalker Tunnel. So over to you, Richard.
Thank you. Well, thanks for that introduction from the low-hanging Mount McGilvray. I'm going to be talking about what we've done over the last 50 years or so with two groups, University of Queensland in Australia, Oxford University, and to understand the evolution of the group and how they found their sort of niches in the world, you really have to know a bit about the history of the times and what aviation was like in the 60s, early 60s when they were getting formed. But in the 40s, aviation was only 40 years old approximately, but they'd already pushed the limits of the primary technologies of the times, which is, of course, was the piston engine and the propeller. You couldn't really do much more with it. Well, they're still around for other roles. The ceiling had been reached for what you could do with that sort of technology. Then the war came along, and that was responsible for an awful lot of development. Amongst it was the development of gas turbine engines, both in Europe and in England, and also in America. The rockets, everyone was developing rockets at the time. Germans really did lead the world, and their V2 rockets set the tone for what happened later that led into the space race. And then, of course, they broke the sound barrier. They were able to go faster than the speed of sound for the first time. I call these proof of concept years. They'd proven there was a future after propeller engines and the technology would work, but then it wasn't really yet ready for mass use. So then in the 50s, I call it technology demonstration. A lot of things happened. Intercontinental air travel became possible, and the pioneering vehicle there, of course, was the British Comet. Supersonic military flight became sort of routine, and access to space started. So there's a transition from transonic, supersonic, hypersonic, and eventually up to space. These things all happened in the 50s, the basic proving ground. There are a few people hanging on to propeller propulsion. This one there is the fastest propeller-driven aircraft. It got to Mach 0.83 or something like that. But that was really for people who hadn't realized things were changing. You look around here, so they got it going. It was primitive, but it worked. And they did it on they had great engineering accomplishments with very little really scientific knowledge, which was great thing to do. But to take it further, a lot of things had to happen. I won't go through this list here, but over the next 50 years, there have been advances all around in gas turbines, rocket propulsion, space travel. But there's another important thing that was happening. You look at all these airplanes, they look like the traditional aerodynamic shape people like to build. And all of a sudden you're in space and there's this thing that looks like a brick. It looks awful. What happened? There's something fundamentally different has happened. And you look at that thing, or something about space travel, that looks like it's been left in the oven too long, like when I try and cook a cake or something, but really it's a flying brick. And so there's a very definite change in technology from these shapes to those shapes. And it's not just a conceptual change, there's a lot of technical detail to understand about it. So as an example of this, how do you build your first re-entry vehicle? A good rule of thumb in engineering is if you've got a new application, try the old techniques, they might just work, and you don't want to reinvent the wheel. So that's what they did in the early 50s when high-speed travel was possible. They built something that was sharp and blunted, and as a re-entry vehicle, it turned out this was no good. It's a bit like, if you want to get down a rope, you can slide down the rope and lose the skin off your your hands, but it's not a good way to do it. You should get a winch or something to lower you down slowly, let the energy be absorbed somewhere else. You can wear gloves, but that's not really good. So what you're doing here is all these streamlined surfaces are going just about parallel to the flow, so any pressure it builds up is not slowing you down. You only got shear stress, skin friction to stop you. So it didn't work. It's like all the heat from coming through to your fingers and burning your skin off your hands. So you've got to go to a totally opposite concept. You put a brick in there, it's got a big bow shockwave that immediately transfers energy to the gas through a pressure pulse. Develops a big force on surfaces normal to the flow, which is going to slow you down, and you're processing lots of gas, so it's all going to get carried away in the airflow, not get absorbed as heat. You still have very high local heat transfer rates, but you can handle that because with this configuration, only something like 2% of the total energy you're dissipating is coming through to the vehicle. So the point of this slide is it was a very big game changer doing that, and lots of new things had to be learned. They did build a brick and flew it, and it worked, but there was a lot of luck and good engineering judgment in those early flights. So to get this new knowledge, you need obviously the scientists, and you need to have experiments. It's not just a question. You can't do the theory till you've worked out the basic mechanisms involved, and for that you need test facilities. But there are problems when you're going fast up into orbit. Total temperatures become very high, much hotter than the sun. Total pressures can become tens or hundreds of megapascals and even gigapascals. You can't contain such pressures and temperatures in a conventional wind tunnel. So what are we going to do? What are the options we've got for facilities? So there's two counteracting effects here. On the horizontal axis is test time. How long do you want to test for? Up to hundreds or thousands of seconds. The other one is how fast you want to go, represented here in terms of total temperature. Evidently, the faster you go, the shorter test time you have. The first wind tunnel that was any use was the Wright brothers one. There's no coincidence that after that came along, flight was possible. They had a few before, but they were so badly made and contrived that the data they got didn't really relate to flight, and they held back the progress of science. Of course, you want to go faster, you've got to get more power, you can get closed-circuit wind tunnels, but really there's a speed limit with these sort of devices just because of the amount of energy you have to dissipate. So there are other options if you want to go faster. We have the blowdown concept, where you get a lot of high-pressure hot gas, put it in a tank, let it exhaust through a nozzle and get a supersonic, hypersonic test flow. They work very well for a few seconds. Speed limit's typically 2 kilometers per second or so. And remember, you need 8 kilometers per second to get into space, 11 to come back from the moon. So you need other options that don't require storing hot, high-pressure gas for a long time. And one famous concept introduced after the war was the gun tunnel, which they've pioneered at Oxford for many years. You basically take a small slug of test gas, heat it up very quickly through a compression of a piston. You get high temperature, high pressure that way. You let it expand out through a nozzle over your flow, and you've got yourself a good test facility. You can get hypersonic flows, get fairly large test times, 50 milliseconds or so. Speed limits are typically of the order of 2 kilometers per second, but they're very useful for working out some of the aspects of hypersonic flight that don't really relate to chemistry, when high enthalpy of a flow is knocking your gas particles apart. The other concept is to go even more extreme and use a shock tube, which is the way we've gone in Australia. They were pioneered by my colleague Ray Stalker back in the 60s, and we're still using the same ideas today. But down here, you're down in the millisecond or less test range, so you've got to look at processes that can be properly established within a millisecond, which is a bit of a challenge. Anyway, to start a good group, what do you need? An enduring group. Obviously, you need good people. And the work for both our groups actually started in MPL in the early 60s. There's Doug Holder from here, who was the head of department for a long time, Professor Schultz, who's my own PhD supervisor here, and Ray Stalker, who was temporarily over from Australia. It was the right time and place. These three geniuses really got together at the same time. They came up with great ideas, and you don't only need clever people, you need team players. One person on their own is not going to start an enduring group and attract more people into it. And all of those people were the same, had that sort of nature. You've also got to be a little bit honest with your colleagues, tell them the horrible truth when they have to know it, And both Ray and Schultz had a bit of a talent for that. One of my first, in the nicest possible way. Like early in my PhD work with Don, he said, "Look, I'm a busy man. I've got nothing more important to do than work with my students. But don't waste my time. When you come to see me, I want to know the conceptual problems, not some grunt engineering detail anyone could find." I said, "That's fine, Don. I'll do that." So halfway through my first year, I needed a very important piece of equipment, which took up approximately half my first year's budget. and on the first time playing around with it, I managed to melt it and fuse it and destroy it. So that didn't seem a conceptual problem to me. I had half the budget. I had half the budget left, and so that's fine. I ordered a new one. Of course, it had to go through Don for approval. He came storming down to the lab, steam coming out of every orifice. He said, what's this? What's this? I said, well, you said you only wanted to know about conceptual problems. He said, well, you've got to learn. Money is a concept. So that was a very important lesson I've never forgotten. Similarly with Ray, I went in the 80s to be his postdoc building shock tubes, and I got carried away by the great things we were doing. I thought of ways we could go faster and higher and all the rest of it. And one time he took me apart and sat me down and said, look, stop running around. Just stop it. I said, what do you mean? What do you mean? He said, you've got to stop lighting fires and do some cooking. And both of those stories were peppered with expressions I can't repeat because they're unprintable, but they got the message across very effectively. Anyway, they were at MPL in the early 60s, producing some high-performance shock tubes, and it was a very productive time. Later on, or not, after only a couple of years, in fact, Holder and Schultz came over to Oxford. In fact, Holder was a head of department when I was here studying. I didn't really get onto his radar, not for anything good anyway, and Schultz was my supervisor. Ray came back to Australia, and again he got a sort of a critical size group going. He had Hans Horner, who's now a professor at Caltech, and John Sandeman, who's a professor at ANU in optical diagnostics. They developed the free piston shock tubes, which is what we've based our group on. And Don came here, of course, with Dougie Holder, and then Terry Jones, Martin Oldfield joined him, and they had a unique and very powerful group, which has persisted to this day. I'm not going to list everyone who's been involved, of course. Anyway, as time went by, we kept in touch. That's Terry and Martin in the early days of the group. Well, not so early. It was early days for me. I was a student there. Ray kept on going in Australia, developing what we call the T-series of shock tubes. And progress continued. That's Martin and Terry joined the group sometime in the 60s. And they had the gun tunnel here. We had shock tubes. Facilities developed even further. They got into piston tunnels. Oxford diversified more than we did. We've stuck in hypersonics pretty well all the way. Oxford have always been strong in hypersonics, and now, as you know, in the gas turbine side of things. So that's not really part of my story. I'm just mentioning it. And we went on developing more facilities. And a lot of students started swapping across the way. There's David Mee, our current head of school, was a postdoc over here in the 80s. Terry Kane, who was a bit of a wild man from North Queensland, did a PhD here, and he's stayed in England ever since. And Peter Ireland joined the group back in the 80s sometime, I think, another pioneering leader. So we started to try and go faster. In Australia, we built expansion tubes, which is a derivative of a shock tube. You cascade extra tubes in series, get more speed, lose out on test time. And again, Terry Jones and Martin devised an amazing number of facilities over in UK that are still in use today. Another generation of students was coming across, Andrew Neely, David Buttsworth in the 90s, who are now established academics in Australia. Now, I had this sort of troublemaker here, Dr. McGillvray. I first came across him as a fourth year student. He was designing a sort of ramjet payload they were going to fly at Woomera, our rocket range. And he was the most annoying student imaginable. He was part of a group, and he said, well, can you support us to go to fly this thing? I said, yeah, we've got $500 for you in a university car. He said, well, I don't think that's enough. So you go and camp and eat the roadkill. You know, don't ask us for any more money, because there isn't any. Next day he came back and, oh yeah, I've been to the dean, it's all funded, you know. And that's when I realised he really had talent. and I hope people take advantage of his talent in Australia, no, this country, England. I do get confused. Now, have you been counting slides? No. Yeah, but one world record holder we have in the group, Martin Oldfield, back in the 70s, I'm told it was originated from some trip to the pub where they were watching champagne corks pop off. He said, hey, we can get these to go much faster in the shock tube. And we did, and they got the record for the world's fastest champagne cork. Actually, I think I've missed out another slide. This was, just step by, this was the young Matt McGilvray when he did fly that ramjet, appropriately named Roger, in Woomera, against my better advice. Okay, this is indicating another era where Terry Kane, his Australian name's Kano, was developing ramjets, and we were able to test one of them on our flight testing program, because by then we got into flight testing of scramjets through sounding rockets, and that was Alan Paul, a pioneer of that technology from UQ, and Kano himself performing over there. Right, this is my last slide. It relates to Martin. As I said, after a day at the pub where I understand Don Schultz was away out of town, he got that great picture. Then back in about 2003, Martin was over in Australia, and again we ended up down the pub, I don't know why, and he was saying, you know, we can do that much faster now. So we went back and students set up a champagne cork, and we got the world's fastest champagne cork at 11 kilometres per second, following on from Martin's work. And we also hold records for the world's fastest cricket ball and the world's fastest golf ball. I know Matt's ambition with this new tunnel he's going to talk to you about is to beat that record, but we'll be doing our best to stop him. And over to you now, Matt.
Thank you very much, Richard. Always a very energetic speaker. Okay, so in about 2009, I came across to Oxford and started working with David Gillespie in the OSNI lab, doing internal cooling work. And about that same stage, we moved across to the new Southwell building located on the OSNI industrial estate. And anyone that knows the group, we've really, you know, taken multiple steps forward by having more space and being able to bring in larger facilities like the OTRF. And one of these facilities was the high density tunnel, which Peter spent his dowry on, you know, in his first couple of weeks back in Oxford, blew away his dowry on the high density tunnel, which we collected out of Farnborough. And this really leads us into the current day. So it's quite amazing that, you know, after generations and generations, how many people have really crossed between the groups in Australia and the groups here in Oxford. And it's really culminated in really our current work on developing these hypersonic tunnels. So if I look at the people involved with each tunnel that have spent time in both countries, and I've actually probably left off Martin Oldfield as well, who's had involvement with some of the free-flying data acquisition work. We've got 12 different people that have spent time in either group. So it's quite substantial. So a real strong collaboration really continuing on today. So now I'm going to talk briefly about what we're doing now. So the National Wind Tunnel Facility Program was set up early last year, and it was led by Jonathan Morrison down at Imperial College. And it's a collaboration between 7 different universities to really provide wind tunnel time to outside academics and outside industry, really for 25% of the time. And to do this, we really need world-class facilities. So what we've been developing here at Oxford is 3 hypersonic tunnels. So it's being led by Peter Ireland with myself. And these 3 tunnels, the low-density tunnel, which is for rarefied flows, the high-density tunnel, which is for hypersonic aerodynamic flows, and the T6 Stalker tunnel, which is our high-enthalpy tunnel. So the T6 facility really is a combination between the T3 free piston driver, which was designed by Professor Ray Stalker when he was at ANU, with the downstream sections of the Oxford Gun Tunnel, which was originally the Bristol Siddeley Gun Tunnel. So we've had to do a lot of modifications because now it's a high enthalpy facility. So firstly, we needed to couple it to the T3 driver, but we also needed to work in new diaphragm stations, and also we've now got to contain 6,000 Kelvin gas in there. So we really needed to look at the heat transfer effects down at the nozzle end. So this is going to be the UK's first foray into the high enthalpy wind tunnel game, but also it should become Europe's highest speed wind tunnel. So we're going up to the 16 kilometers per second type speeds. So there's 3 different modes of operation that we're going to be running in this facility. The first 2 are a reflected shock tunnel and an expansion tunnel here. They're both for testing subscale models. So typically we try and do some match some non-dimensional parameters. So typically here in hypersonics, the things that we try to match is total enthalpy, gas composition, and density length scaling. If it's a slender body, we also do Mach number. Blunt bodies, we tend to not worry about the Mach number. So as Richard alluded to, a reflected shock tunnel, although it gives you much longer test times, it's capped at about 6 kilometers a second. If we want to go for faster speeds, look at lunar return conditions, we really need to go to an expansion tunnel type of mode. The final one is a shock tube mode of operation, and that's when we start to look at radiation. Because radiation doesn't scale with density length, we need to actually look at it full scale and the appropriate pressure. So to take you through some of the free piston driver work, it's probably best to look back at Ray Stalker's time when he was at Ottawa at the NRC back in 1958. So that's where he did the pioneering work for a free piston driver. So he realized that although there was other options out there to drive these shock tubes, you could heat up some hydrogen, you could have a detonation, these weren't really practical in a university environment. I don't think we can quite get those things past our IHNS officers here. So he still needed something that gave him high pressure, high sound speed gas. So he started developing these free piston drivers. And when he went back to ANU, he kept working on these and improved upon it. So he started looking at the piston dynamics. How can we get rid of some of the annoying effects of, well, the pressure drops and we decrease our test time at the end because we get these rarefaction waves coming down. And he started looking at matching the piston speed to the speed of the gas once it actually exits the end of the tube. So it's not just a fluid dynamics problem, it's really a structural problem as well. This thing has 1,000 ton of loading under the piston decelerating at 10,000 G. So he was an amazing engineer to overcome some of these issues. So this is actually the T3 driver where it was when we purchased it off one of Ray Stalker's contemporary, Don Fry, standing here. And we brought it over here middle of last year. And this is actually the single point lift to bring it into the OSNI lab. I was quite worried at the time that, are we going to be structurally damaging the thing, having it in cantilever or rolling it across the floor? And Richard just started sending me pictures of battleships. So after that point, we were convinced, oh yeah, it's nearly the same size as the Bismarck, it should be okay. So the first mode of operation is really the mode that the T3 facility operated in, and that's a reflected shock tunnel. And that works by having our test gas sitting in a tube. We send an incident shock through it. So if you look at the distance time plot here, we move from region 1 to region 2. So we accelerate and heat up our flow through an instant shock. We bring it to rest with a reflected shock. And if we have some tailored condition across our a tailored driver condition, we should get a nice long test time here of 1 to 5 milliseconds to utilize. Now, one of the biggest interests is air-breathing engines to test in these facilities. And if we look at an altitude versus Mach number plot, there's really a corridor they want to fly in, somewhere between 100 kPa, which is the structural limit, and 25 kPa dynamic pressure, which is the combustor flame out limit. So if we look at a unit Reynolds number capability of our facility, we can really develop these things up to Mach 10, do some of the fundamental research behind these air-breathing engines, which hopefully one day will allow me to go have a surf in the afternoon down at Bondi Beach and get back here for a lecture in the morning. So Richard did a lot of the pioneering work. After NASA kind of gave up in the 70s, Richard came back to the same idea in the 90s on expansion tubes. So there's 3 limitations for a reflected shock tube in going to higher speeds. The first is structural. You have to start containing massive total pressures. The second is heating up the nozzle throat. So you're going to have temperatures up above 10,000 Kelvin. But those 2 you can overcome with engineering solutions. The third you really can't, which is the flow then wants to expand out to the nozzle so rapidly that you actually don't have time for it to chemically recombine back into clean air. So that rapid expansion process you really want to avoid. And the method of doing that is really to couple 2 tubes together. So your test gas undergoes an incident shock like it did previously in a reflected shock tunnel, then undergoes an unsteady expansion out to your conditions. Now across an unsteady expansion, you get a multiplication of your total enthalpy and your total pressure, allowing for massive speed gains. So we can now start getting up into the region where we're looking at peak heating for several different missions from far solar system to lunar return. And so we're able to cover these 6 to 15 kilometers per second return conditions to Earth. The final mode we've got is shock tube. And in this mode, we really make an analogy between the stagnation line radiation emission to that seen behind a shock traveling down a tube at very high speed. So here, if let's say we wanted to do lunar return at 10 kilometers per second, that would be about 0.2 torr pressure. So we fill up our shock tube with 0.2 torr, which is about 1/4 of a millibar, with air, and then we race a shock down at 10 kilometers a second, and we capture a very quick image of what's going on. So we stand still, so it looks like the shock's stationary. We can make an analogy between what's happening on the stagnation line here and the radiation emission behind that shock. So as you can see here, our facility here can cover pretty much everything from Mars return all the way back to the lunar return type of conditions. So unfortunately, Ray passed away early last year after we had his tremendous support in getting the T3 driver over here. So we'd like to recognize Ray and all his pioneering work and all his fabulous students and really inspired engineers over the years. Thank you.